If you climb a mountain, starting at 0 meters and hiking to the 3,000-meter summit, there is a physical reality to your journey. You cannot teleport. At some point, you were exactly at 1,000 meters. In mathematics, we call this continuity. A continuous path has no jumps and no gaps. If a second climber magically skips an altitude, that path is broken. Only continuous functions guarantee a connected journey. Because you moved smoothly through physical space, you had to pass through every single elevation between the base and the peak. This human intuition translates directly into mathematical certainty. Looking at this graph, we can formalize that intuition. Take any continuous function defined on a closed interval. It starts at point A with value p and ends at point B with value q. Pick any target value between p and q, call it m. Because the function is continuous, there must be at least one input where it hits m exactly. This is the Intermediate Value Theorem. It proves that a specific intermediate value is reached without ever requiring us to calculate exactly where it happens. Consider the equation x cubed minus x minus 2 equals 0. Finding the exact numerical solution to a cubic equation like this is difficult, but plotting this on a graph, we can test its boundaries. If we plug in an input of 1, the result drops to -2. If we plug in 2, the result rises to +4. The function is a polynomial, which means it is continuous. It starts below the 0 line and ends above it. Therefore, it has to cross 0 somewhere between 1 and 2. We did not solve the equation, but we used logic to prove a solution exists. Proving that an answer is there shifts our effort from calculation to logic. This number line highlights our target area. Now that we know a root is trapped between 1 and 2, we can hunt it down. We cut the interval exactly in half and test the midpoint, 1.5. The result here is negative, which means our solution is squeezed into the upper half, between 1.5 and 2. If we test the next midpoint at 1.75 and it returns a positive value, which half holds the solution? The solution is now bounded between 1.5 and 1.75. Every time we repeat this process, we cut the search area in half. With each step, the precision of our answer doubles. 10 steps yields 3 decimal places of accuracy. This systematic trapping is called the Bisection Method. It is a reliable root-finding algorithm because it only depends on the sign of the function, ensuring it converges on a solution even where complex methods fail. Imagine 2 people climbing the same mountain on the same day. One starts at the base and hikes up. The other starts at the summit and hikes down. Was there a specific moment when they were at the exact same altitude? Instead of tracking 2 separate paths, we defined a new mathematical relationship. We subtract the descending climber's altitude from the ascending climber's altitude. This is a difference function. At the start of the day, this difference is negative. At the end, it is positive. Since they moved continuously, that difference function must pass through 0. Defining this new relationship proves that their paths crossed at the exact same height, at the exact same moment, even if the actual time and location remain unknown. Looking at this discrete number line, we hit a structural limit. This theorem fails if we only apply it to rational numbers, numbers that can be written as fractions. An irrational solution like the square root of 2 simply falls through the microscopic gaps between the fractions. To fix this, we rely on the real number system. Real numbers possess a property called completeness, meaning every possible gap is filled. This completeness is what allows limits, derivatives, and the theorem itself to function. Without it, the logic of calculus would fall through the gaps. We can scale this difference function up to the entire planet. By tracing any continuous ring around the Earth and comparing opposite points, we can prove that right now, 2 exact opposite points on the globe share the exact same temperature. This cheat sheet summarizes why. You need a continuous function and a closed interval. Together, these conditions guarantee an intermediate value exists. In the next video, we apply this logic to the rate of change. This is the mean value theorem, which guarantees that a function's derivative must hit a specific intermediate point. Mathematics is highly focused on calculation, but its deepest results are existence proofs, logical frameworks that prove an answer is undeniably there, even without pointing to it.